In this video, we extend our product concept for vectors to a new product, the dot product. And it's written as one vector dotted with another vector. We contrast that with the scalar product, where we have a scalar times a vector. That would be something like 3 times some vector versus a vector times another vector. It immediately becomes apparent that we can't do dot products the way we do scalar products, at least with your thinking of components. It makes complete sense to talk about 3 times a vector, and we interpret that as the vector plus itself 3 times. But if we have a direction multiplied by another direction, that intuition breaks down very quickly. So we're going to have to do something different. The definition of the dot product, when it combines these two vectors, the first thing to note is that the output of a dot product is a scalar value. So we have 2 vectors in, and then we get a scalar out. So that's already quite different. Next, we talk about the angle between the vectors. Again, each of these vectors will have a direction, so it makes sense to talk about the angle between them. And if we take the smallest angle possible between them, so 0 to pi radians or 0 to 180 degrees, and we can always do this, it would be this side of the angle as opposed to this longer way around. We don't use that side. But if we always use the smaller angle, then we define the dot product as the length of v times the length of w times the cos of the angle between them. So notice that the lengths play a role. So in some sense, this is why it feels like a multiplication. We're taking the magnitude of those 2 vectors and multiplying them together to get potentially a longer vector. And the change to handle the fact they have directions is built in here. Cos of the angle between the 2 vectors. All right. Then if we take a look at the vector I, well, that is the vector that goes along the x-axis direction. So if we draw a quick sketch here, and we draw the I vector, which has length 1, then I dotted with I can be computed using this formula. Take a moment to consider the options there, and then we'll check in. All right. Clean that up a bit. So I dotted with I, with vector notation there, would be the length of the I vector times the length of the I vector again, so nothing too sophisticated there, times the cos of the angle between them. Well, the nice thing about these 2 vectors is that they're identical, and so there is actually a 0 angle between them. Then we can go down this list and say, well, the length of I is 1. This length of I is also 1. And the cos of 0 is also 1. So the dot product of I with I gives us the value 1. And note again that this is a scalar value that we get back. So that points to C as the correct answer for this particular question. So if we have 2 vectors here and we can figure out the angle between them fairly easily, this formula is quite helpful. What if you did the same calculation with I times j, and recalling that if we draw our usual axes, x and y, then the vector I goes that direction, and the vector j is in the direction of the positive y-axis. So take a moment to consider that, and then we'll check in with the answer. All right, so the same basic process. We take I dotted with j. That's going to be equal to the length of I times the length of j times the cos of the angle between them. In this particular case, though, the angle is going to be in radians, pi over 2. All right, so we have length 1. All of these vectors are unit vectors. And then we have cos of pi over 2, but cos of pi over 2 is 0. So this dot product here gives us a 0 value. Fair enough. That means B is the correct answer. What we'd like to do as we go forward is gradually add some interpretation to this. What does it mean to have a dot product of 1? What does it mean to have a dot product of 0? We'll build up to that. But for now, it's worth exploring a common feature that we use with dot products, And that's imagining that our two vectors v and w are perpendicular to each other, just like I and j were, but possibly of different lengths. But the key thing being an angle between them of pi over 2. Well, if we have that guaranteed, then we're going to have the length of v times the length of w times cos of pi over 2. If we have perpendicular vectors, cos of pi over 2 is always going to equal 0. And so regardless of the length of those two vectors, we're going to have a 0 dot product. And so that tells us for any two perpendicular vectors, v and w, the dot product is equal to 0. Let's put the product in there. All right. So that's an important feature. The dot product of two vectors, if we end up with the value 0, indicates presumably that they're perpendicular. Well, actually, it's not quite true. That's almost true. If we have v times w equals 0, and we have that equal to the length of v times the length of w times the cos of the angle between them, it is certainly possible that the cos of theta equals 0. And if that's the case, then the vectors are perpendicular. However, that's not the only way that could happen. It's also possible that the lengths of v or w are also 0. So if one of our vectors is the 0 vector, then we would also get a 0 dot product. So that's an important distinction to remember. If we see a dot product equaling 0, most of the time in practice, it's because that we have two positive vectors, two vectors with non-zero magnitudes. And if that's the case, then the two vectors have to be perpendicular. However, we do have to keep our options open and recognize that if one of the vectors was the 0 vector with no direction, then we also get a 0 dot product. We will see cases where we encounter both the lengths equaling 0 or perpendicular structure, perpendicular relationship between the vectors as we look at dot products going forward.